Today I'll be talking about our study on designing and controlling pumped thermal energy storage systems um, that can deliver high-grade heat through heat integration and that can aid in industrial decarbonization efforts. So this talk will be divided into two sections. First, I will introduce what thermal energy storage is. I'll give a background on energy storage in general, and then what can we do with these technologies to robustify a renewable heavy grid. And then in the second part, I will talk about how we can use the advantages of thermal energy storage to decarbonize the industrial heat, basically. So again, I'll start with a background on energy storage. So our efforts to, again, decarbonize the world economy and to meet our climate goals require an ever-increasing share of renewables in the energy grid. Replacing polluting fossil energy with renewable alternatives like wind and solar will help significantly reduce carbon emissions, as we all know, but it creates a reliability issue in the energy grid, which is due to the inherent intermittency of renewables. As we increase the share of renewables in the energy grid, the amount of dispatchable energy sources become scarce, which puts a strain on the energy grid. So we need to meet this energy shifting demand that arises from day to night or from summer to winter, for example. This is where energy storage becomes very valuable. Currently, this shifting demand is being met with non-renewable sources such as coal and gas and nuclear, which can be called like baseline sources. The reason for this, again, is that at times of energy supply variability, we need dispatchable energy. So we can ramp up and ramp down coal and natural gas power plants. Not so much with nuclear, but it's just the baseline for that again. Or with pumped hydro storage. But with energy storage, renewables can be made dispatchable as well. The largest share of energy storage technology in Europe is occupied by pumped hydro, which is almost around 95%. But this offers limited areas for expansion because it's an expensive endeavor to build these pumped hydro facilities. Also, there are limited spaces available, so we can't really build one in London, for example. So there's an increasing need to diversify our energy storage capabilities with technologies such as redox flow batteries, lithium-ion batteries, sodium batteries, as well as hydrogen generation and storage and its derivatives. So I'd like to separate these energy storage technologies into three different areas. First is the short duration. So this is from seconds to minutes. It can be used to provide frequency regulation, emergency response, and it's again, this is response within seconds to minutes. And this is where lithium-ion batteries or other similar battery technologies come in really handy. But these technologies are harder to scale to medium duration or long duration storages because as we increase the capacity of like a battery pack, we also need to add so to increase the storage capacity, we also need to increase the power core basically because they're coupled. So these are expensive to scale up. Also, they use really rare elements and that they're not really environmentally friendly. On the other end of the spectrum, we have long duration, like really long duration, seasonal storage. So storage between summer and winter. And this is where pumped hydro comes in really handy with its high capacity. Also hydrogen and its derivatives, so ammonia, methanol, so electricity to fuel, so that we can convert the excess electricity that we have and store it as fuel in our tanks. But these technologies also have low efficiency because we convert electricity to fuel, from fuel to back to electricity. Again, and this is not really applicable for the middle side we have. So this medium duration storage, we can call it, is days to weeks to maybe months. And we can do this, with these technologies, we can do load following, peak shaving, and then arbitrage. So that we see like a 7-day curve. I think this is in Germany. So we have this variability, and I showed this a few slides back as well. And this can be met better with flow batteries, which have decoupled its power cycle and the storage capacity, basically. Or coming to the main topic of the talk, we can also address these with thermomechanical energy storage technologies. So these are liquid and compressed air storage, or again, thermal energy storage. So these can be scaled up and scaled down quite well, and these don't really have geographic restrictions on them. Another reason to diversify our current energy need is that our current arsenal of renewables and the energy storage technologies cannot offer the same energy flexibility that conventional technologies can. For example, solar and wind power are electricity only, or mostly electricity only, and cannot offer, for example, grid inertia or again dispatchability. Whereas a conventional gas powered or coal powered power plant can provide this grid inertia with its spinning reserve, and again dispatchable with its ramp up and ramp down capabilities. For profitable energy grid operation, these energy flexibility or revenue stacking opportunities need to be pursued. So these can be again load following, peak shaving, frequency and power control, as I mentioned earlier. An additional source of revenue becomes available and at times necessary for energy storage operators in these cases, and this allows for increased utilization factors of these energy technologies, and is essential for again profitable operation. What we chose to focus on again is thermal energy storage. It boasts variable capacity, so we can change the capacity of it by just adding tanks on it. I'll get to the details of that later. And it has high utility. It can deliver electricity and heat. And that is the most important ability in our view of its ability to deliver heat. It is under development in It is under development in many parts of the world, with several projects being planned at the moment. I know of some in America, in Alaska, and Wisconsin, but there are many in Europe as well. So it is a ripe area of research. So more specifically, if we look at pumped thermal energy storage, or PTES for short, what we see is that it is simply a heat pump on one side and a heat engine on the other side. So when we want to charge the system operates as a heat pump, taking in electrical power and some low-grade heat as the heat source, and creates a temperature difference between two reservoirs. So we have hot thermal storage and cold thermal storage. And then when we want to discharge this heat or get the electrical power out, we operate this as a heat engine. So the hot thermal storage is our heat source, and the cold thermal storage is our heat sink. And then we also have some heat rejection due to inefficiencies in the system, but we get out this electrical power. Its operating principles, as you might have guessed, is similar to conventional thermal power plants, which are presently being used to meet this variable energy demand. PTES can ramp up and ramp down just like the conventional plants, and this similarity allows for decommissioned power plants to be converted to PTES facilities at a fraction of the cost of building a totally new one. So that was some background on again thermal energy storage, thermal energy storage, and so on. So I'll start with what we did in this project. So we started with building a model in Aspen HYSYS, which we use a lot in the chemical engineering field, and we modeled this as a closed cycle with the turbo machinery and the heat exchangers. We didn't model the tanks in Aspen because that requires a dynamic model or time dependent model, but it's the the system has its basics rooted in established technology. I think the first patent on this was taken out in the 1920s, so it's a very well understood, but it's not been explored. So as I said, while charging, the system operates as a heat pump. The working fluid goes into compressor, goes to high temperature and pressure, exchanges its heat with the hot side, goes through the recuperator, comes back, expands through the expander, and then goes to the cold side, receiving heat from that, and then goes through the recuperator again, closing the cycle. The recuperator here is to extend the operating range, basically. It allows for decoupling basically this temperature to this temperature and this temperature down here. So they don't really depend on each other because we have this internal heat exchange. And then on the discharge cycle, the system operates in reverse as a heat engine generating electricity from the turbine. So I mentioned the working fluid. So the thermodynamic cycle we use is a Brayton supercritical CO2 Brayton cycle. So as you may guess, the working fluid is carbon dioxide, and it has a high density around its critical point, so or above its critical point, so that we can get smaller turbo machinery when we're operating this machine. So one advantage of that is this basically. If you imagine a power plant with the huge compressors and turbines, the scales we're talking about here is small. I can there's a video. There's a video online of some researchers from Southwest Research Institute who built 1 megawatt scale supercritical cycle, and the compressor that they have is able to fit in the person's hand. So they're tiny compared to the technology that we have right now. It's again investigated thoroughly though. Another advantage of this cycle is that I will compare it with another cycle now, but in a moment. But we can have sensible heat storage in both sides, or mostly in the cold side, so that we don't have phase change in the carbon dioxide or the working fluid, so that we don't need to have phase change in the cold side. So comparing that to a transcritical cycle, for example, we have this phase change down here in the cold side. So we need to store the cold side as a phase change material, so an ice slurry or something similar. So that limits the available technologies for us on the cold side. So it is beneficial to operate in the supercritical region. In the design that we have, the hot storage is a molten salt mixture called solar salt. It's widely used in concentrated solar power plant industry. So it has high density, it is safe, it's a proven technology. So we deemed that it was adequate for us. And then on the cold side, we have just ambient pressure water. So it's not pressurized, it's not steam. It's just, again, it's abundantly safe. It has a high heat capacity, so the tanks won't be as huge as other technologies. Now, the most crucial components are the turbo machinery here, so the compressors and so the two compressor turbine pairs, one for the charging, one for the discharging cycle. I'm saying these are the most crucial because the most inefficiency or the most restrictions come from these machines. So the inlet conditions of the compressor or the turbine are the most important in determining the overall efficiency of the system. So because these are really crucial, modeling these components accurately is also is really important to the part load or our understanding of how the model operates or the system operates. So we modeled the compressors using compressor maps adapted from literature. So these are hard to find the right size and from industry because they're mostly like proprietary information. So we need to have some way to model these. So this is what we did. So the next stage is, after we model this process in Aspen, we want to look at how we can operate the system in part load conditions. So how can we go down in power when we need to operate, when we need to charge with low power, or how can we go up in power when we want to have discharge of more power, basically. And this brings us to state of charge management. If we didn't need state of charge if we didn't need to operate in part load condition, we wouldn't need state of charge management. It would just be the balance would be set in the system. So this is again divided into two sections. First is in-cycle state of charge management, and the next is the other is this cycle-to-cycle state of charge management. I'll get to the details of that, but the first one ensures that the storages, so the hot side and cold side, don't run out before each other. And the second one ensures feasible operation over a given time horizon. I'll start with in-cycle state of charge management. This was built in, or this was implemented in Aspen again, so in the software. The goal here is to ensure that neither the cold or the hot side or the cold side run out before each other. So when we're charging the hot side from 75% to 80%, the same happens on the cold side as well. If we let this system be, this won't happen. It will just be charging at different rates. The method involves adjusting storage flow rates. So the flow rate going from here to there, and then from T8 to T7 to T8, basically. So that the discharge times or the rate of change is equal at a given moment, at a given design condition or operating condition. First, some of the variables are predefined. So these are the temperatures of the storages and the pressure of the lower side. This forms the basis of the simulation, and then we determine the part load condition depending on what power we want. So we change the speed and the mass flow rate of the compressor, and then that allows us to basically set what power we want to operate at. With these information, we can get we can solve the rest of the system by giving the basically independent variables into the system, which determine the flow rates. Here, the temperatures are varied instead of the flow rates because Aspen is kind of finicky in terms of when it comes to changing the flow rates and the optimization problem. But the temperatures basically simulate the change in the flow rates. So to balance the two sides, as I said, an optimization problem was designed, and the objective here is to minimize the difference between the operating times of the two sides. As a result, at each operating condition, so we can set whatever condition we want to have on the charging, on the compressors or the discharging compressor. And then this ensures that the rate of change of storage capacity at the two sides are equal. So again, if we go from 75% to 80% on one side, the same happens on the other side. If the system was again operating at a fixed power input, so we didn't have part load operation, we wouldn't really need this state of charge management algorithm because it would just be balanced itself. It'll be operating at the same given condition. But when we change conditions, that the balance is thrown off. So using this state of charge management algorithm, we generated some data points from the Aspen model to get to have a surrogate model of this system, so that we can use this surrogate model in further optimization problems or further simulations to investigate other aspects of this system. Which brings us to the cycle-to-cycle state of charge management, which is the goal is to ensure that the system doesn't overcharge or over discharge throughout the simulation horizon. So let's say we give it 5 days to operate, it doesn't overcharge or it doesn't discharge. It doesn't charge over 100% or discharge over below 0%. The objective function here is given as is the minimization of or maximization of operating profit. So we're not including capital costs in this, or that's a different that would be a different study. We take the electricity price data from the UK grid for this, and we can simulate if we let the system vary the charging and discharging powers, we can have it can decide what to do with within the time horizon. So, and again, these two constraints basically ensure that this state of charge is within within the limits that we set. So with the optimization problem formulated, we conducted 4 different case studies, all with different starting and ending conditions. So, for example, this starts at empty, ends at empty. I'll get to that in a minute. I'll get to different layout in a minute, but this starts at empty, ends at full, and so on. So we can see that the green here shows the electricity price profile. So when the system charges basically when electricity price is low, and then this charges when it's high. So it operates in a profitable and feasible manner. In most of these scenarios, the round trip efficiency of the system is around 55 to 60%. So we have comparable results with similar technologies. And then we can look at the state of charge of the system overall over this, again, 5-day time horizon. And we see that, so the red shows the salt tank and the blue shows the water tank, but we see that they're really overlapping quite almost perfectly. And the reason, and this for us shows the power of, or the feasibility of the state of charge management algorithm. Both in cycle, so we see that it only deviates around 0.3% at the end between them, and then over the whole horizon of the whole simulation, it doesn't go over the limits or below the limit. So again, both of the state of charge management algorithms work quite well. And then finally, so these simulations were a test for the system if it works or not, but then the real application or real case study could be something like this, where we have this PTES system coupled with a wind farm, for example. So in this case, the problem is it's altered a bit. So we have a wind power profile given. That's again from the UK grid. And it's averaged out to a 5-day range, and it's I think averaged from last year 2023, and the difference here is that the system only charges with wind power, so it doesn't it cannot charge above whatever wind is available. So as you can see here, it used to want to have go to maximum here, but now it just goes to it is basically limited by the wind power that is available, and then it can discharge whenever it wants again. And if we look at the figure on the right, we see that it's and then it sells whatever is excess. So if it doesn't charge, it sells the wind power, and then whatever is left after charging the wind power, it also sells. So we see that, for example, in this region, maybe I should use the pointer. In this region, we have low electricity price, so it doesn't want to sell the wind, but so it charges during that, and then it basically discharges when electricity price is high. So if you look at the blue line, which was the wind power originally, and then compare it with the orange line, that's the dashed line here, we see that the wind power is basically shifted from day to night, or night to afternoon, late afternoon, late or early evening, basically. And this happens most of the. Yeah, this happens almost every day. So again, this shows how these storage systems can allow for dispatchable wind power or renewable power. So that kind of concludes our first section of the talk on energy storage and how we can help with dispatchable renewables. And the second part focuses on heat integration and heat decarbonization. So again, I'll start with a small background information. The global heat demand is around 52. So the energy that we use in globally, 52% of that goes to heating things up. So or cooling, basically, heating, cooling. So this might be in industry, this might be in it can range from cooking at home, heating this building that we're in, or huge industrial furnaces and reactors. But the problem is, if we look at the supply of this energy, and this is from the International Energy Agency, almost 73% of that comes from fossil fuels. And again, this is the supply of heat. We have electricity at 5%, but it's also non-renewable sources. And then we have traditional use of biomass, but then again, it's also burning wood and timber and such. So we have a really small amount of purely renewable sources that we use in this heating demand. So if we dive deeper into this data, if we look at the buildings and residential heating sector, we see that around almost exactly 50% of the heating demand is supplied by non-renewables or fossil fuels. But if you look at the grid electricity, well, it's not 100% renewable source electricity, so it's also coming from some natural gas power plants, so it's also not renewable. And then bioenergy as well, it's also not exactly biofuels and so on. So in the end, the amount of total share of renewables, or we can say comfortably, in building heat supply comes to around 15%, sorry. And residential heating is on the lower temperature ranges, so around 50 to maybe 150, 120 degrees, which can be quite comfortably met with district heating, which includes heat pumps and so on. But when we look at industry, the outlook is much less pleasant. So around 70% of industrial heat is supplied by fossil fuels, and this is mainly because of the medium and high temperature heating requirements of industry. So if you look at the low temperature heat, it's kind of similar with, sorry, why is it? If you look at industrial, the shares are kind of similar with the low temperature heat, or with the buildings and so. As the required temperature increases, the possibility of using renewables, as we can see, or the available renewable sources decreases. And the reason for that is, well, fossil fuels have a big advantage in that they are excellent at releasing their chemical energy as heat. So when we want to have a cement production plant that operates at 800, 900, or 1,000 degrees, we can't really get that with renewables in the current scheme of things. So to summarize this, decarbonizing and basing heat on renewables is a hard to achieve sector at the moment, especially with respect to industrial heat usage. So on average, only 13% of the heat usage can be reliably delivered by renewable sources. And again, this is also on the lower temperature side. And then there's also a discrepancy between the buildings and industry. So again, what can we do about this? If you look at some ways of providing heat with, again, because we're also talking about energy storage within the energy storage schemes, we can start with gas boilers or gas boilers with carbon capture and storage. There's a marginal price increase, but we get carbon reduction. But these are, again, not renewable sources. If we look at more greener alternatives with hydrogen biomass, or if we generate hydrogen and use that in the boiler, or biomass in the boiler, but we see that hydrogen has, again, efficiency problems, and also it's really expensive to implement in this case. Next, we can look at how we can use lithium-ion batteries again in electric boilers and heat pumps. So we store electricity in lithium-ion and then in batteries, and then use the electricity there to provide the electricity to the heaters. But we see that again, these are really again, especially the electric boiler is really expensive with the batteries again, and these are not really sustainable storage technologies. So finally, we can look at thermal energy storage. Here, the thermal energy storage system replaces the lithium-ion battery, basically. And we see that there's a reduction in levelized cost of energy, electricity here, or steam here. And again, this only looks at steam production. So again, lower end, but this gives you an idea of what the technologies available are. So how can we implement these technologies in industrial settings? Let's say we have a process and with composite curves like this. So I'll give a bit background on composite curves. I'm not sure if everybody is familiar with them, but basically what they do is represent the hot and cold streams available in a process in a single diagram, where the streams that need heating can be matched with streams that need cooling. With this, we can build heat exchange networks, and we can limit the amount of cooling and heating that we can provide. So let's say if we didn't have heat, or I'll give a more solid example here. Let's say we have a reactor. It's a really simple and crude diagram, but let's say we want to have this. The inlet of this reactor needs to be at 200 degrees, but the feed is around 50 degrees. So we use a heater to heat it from 50 to 200, goes through the reactor, and then we get 250 degrees out. And then, but the product needs to be at around 60 degrees. So we use a cooler for that. But what we can do instead is, if we match these streams, if we reroute the outlet of the reactor and you pass it through the heat exchanger with the inlet, we can limit the amount of external utility that we use and basically save energy. So these composite curves allows us to do exactly that. So and in this case, if these are matched, so these parts are matched, so that there's internal heat exchange, but then the remaining cold streams need to be heated, and the remaining hot streams need to be cooled. And we'll be focusing on the heating requirements for now. So if we go back to the same diagram with, if we go back to the PTES system, how can we implement these systems in a heat integration scenario? Well, we have a hot side that is around 420 to 560 degrees, so we can use that in these medium temperature ranges in industry. So implementation of this heat integration involves addition of 2 more heat exchangers, one to supply the heat from the hot side to the cold side, and then one which is a bit counterintuitive, but supplying also some heating to the cold side as well. And the reason for that is, as I mentioned, there's a balance between these two. So if I go to the next slide, this gives you a better idea. So we take some hot salt from the salt tank, and then we use some of it to go to the process, and then it gets discharged. But then we need to use some of it to heat the cold side. If we don't have this balancing cycle, what we'll have is, let's say we discharge this tank 20%. It's at 80%, but this is at 100% now. And we want to charge again. Well, this can be charged, but this cannot be charged anymore. So we need to be able to discharge this because we're bypassing the discharge cycle, basically. So that is something that we need to keep in mind. So again, if we supply the heat with the cold side, with the hot side, and if we add that hot side onto the composite curves that we had, we get this diagram. And we use it to exactly fill in the heating requirements. We use a similar optimization algorithm, this time adding the heating elements in there as well. And the heating draw basically and the balancing cycle is implemented in equation 2. And then we can use similar case studies again with a 5-day time horizon, and then see what the results are. So again, we start with a baseline. So this is the same as the studies that the cases that we saw in the beginning. There's no heat supply. It's just electricity in and out, electricity in, electricity out, and round trip efficiency around 61%. Well, if we look at the second diagram on the right, on top right, we see a constant stream of constant heat supply that is given to the process. So again, this is similar to being integrated into a process, and we see that because of that, the SOC or the charge indication basically goes down constantly. So it needs to charge more and more to basically mitigate this effect or counteract this effect. So if we look here, for example, there's no charging at this time, but we get some charging here on this diagram. So and then finally we have so this is the most applicable scenario. We also have a variable heat supply, so we let the system vary how much heat it wants to supply. But this again requires a heating price. So heat price, which is harder to gauge. It's not really easy to. Sorry. It's not as easy to arbitrate as electricity because it's not as transmittable as electricity. So, but we can have a similar study there. Depending on the heating price, it either doesn't want to charge this discharge with heat, or it also only discharges heat. But if we look at the again the results here, we see that as we increase the amount of heat that we supply, we also have an increase in round trip efficiencies. Now, some of you in the audience might say, "Well, that is expected. That's basically what we're basically doing is cogeneration, which is an established technology in again conventional thermal power plants. So if a coal-fired power plant or a natural gas-fired power plant naturally operates at a round trip efficiency of around 30, 35, 40%. But if we increase the if we use the waste heat that is produced in the burning of the fuel, then we can increase the round trip efficiency or the general efficiency around to 60, 70%. So that is what's happening here as well. As we increase the heat supply, we get more and more efficiency. And we can also look at some CO2 considerations. These values are approximations, but what we can say is that the total amount of heat that we supplied here, for example, if that was supplied by fossil fuels, this would be the amount of CO2. So we can say that if the electricity used to charge the PTES system, or the heat pump system in this case, is purely green or mostly renewable, then we can say that we're saving around 120 tons of CO2 just in this 5-day simulation. And then as we use more energy, we get more CO2 reductions. And then finally, I'd like to touch on multi-temperature heat supply. So there are two reasons for this. There are two reasons to look into multi-temperature heat supply. One is that there are many processes that require different temperature levels. So this might be, again, there might be some drying and also a high temperature reactor in the same process. So we need to provide the same. We need to provide both temperatures at the same time. Or on the other reason is that the heat supply using the molten salt that we have, as I was showing here, might not be able to match the process exactly, for example. So this is it would be better to have this closer to the the cooling demand that we have, because we're wasting some energy in this region, or exergy. And then also we also have that. I mean, I'll get to that. So again, if we look at temperature levels and used in different industries, if you look at temperature levels used in different industries, we can have a wide range of temperatures requirements, or temperature requirements, basically. Yes. And then if you look at the temperatures that can be supplied by power technology or heat supply technologies, they also have these different varying applications. So we want to implement PTES systems in a range where we can supply a wide range of temperatures that can be applied in many situations. So if we go back to this diagram, this source where let's say we're supplying again heat from the hot side, again, and using some of that to discharge cold side, basically. Well, if we didn't do the balancing, the COP would be around 1.46. But since we're using some of that heat to discharge the cold side, the actual heat that we supply is lower, so the COP is actually lower around 1, which is not really beneficial. To improve the COP and the efficiency as a result, we can use a similar Brayton cycle, just shifted down in the TS space with a lower temperature and pressure operation. This will be a dedicated heat pump with storage. So again, this is a separate. This is implementing the same technology, but with different resources, basically. And we envision this to be operating in the same plant, for example. So we'll have. I'll show that later. But what we have is on the hot side now we have thermal 55, which is a thermal oil. It was chosen to represent any thermal oil, so it's not specifically thermal 55 that can be used, but the temperature ranges matter. The operating temperature ranges matter. And on the cold side, since we're only going to charge this system to the hot side. We're not going to be discharging it as electricity, so we don't really need to store the cold side. So there's no need to discharge the cold side when we're using it as a heat source. And so we can use ambient air, ambient water, depending on the layout that we need. In this case, we're using ambient water because this heat exchanger already uses water. We want to reuse as many of the equipment that we can, so that we don't. Otherwise, we would be building a different heat pump, which wouldn't be interesting. So, and again, it is crucial to use the same equipment. And what we want to look at is the turbo machinery, because that's, I mean, the inlet of the compressor here is up there, and then we need to be able to see if the compressor can operate at a lower inlet conditions. We try to keep the thermodynamic properties similar, and we also have a study coming up that investigates this as well. So, and if we implement this terminal or with oil, we see that it doesn't perfectly match again, but it better matches the cold side in this study. In both cases, the hot stream provides around 132 kilowatts of heating to the cold side. So again, we adjust this optimization problem slightly. I'm not going to show the same equations again, but we see that if we supply the same amount of heat or the same constant heat supply over the duration, we see that the operating profit is around 13,000, and the COP is around 1 when we use the salt, only the salt case. But if we look at the heat pump with storage, in addition to the PTES system, we see that the operating profit actually increases, and then the COP increases as well. So what we see is that the electricity is still satisfied. Electricity requirements are still satisfied. It charges at the same times and discharges at the same times with the salt, but at the times when it wasn't normally operating, it now operates as the heat pump with storage, so that it can supply that heat from the terminal side. And the good thing with this is that we get a higher utility, the utilization factor goes up with this basically. So we have the same system can be used more times. And this is again a simpler study, but we have another study coming up that we submitted a paper for, where we have multiple heating requirements: high temperature, medium temperature, low temperature, and multiple heat storages basically. So we have again salt, thermal 55, and another thermal oil, where the system chooses which one to discharge and which one to charge at a given moment. So it shows the capability, but the most crucial thing again is to investigate the turbo machinery. And being chemical engineers in this, we're not really that knowledgeable in that, so we're collaborating with the mechanical engineering department on that at Imperial with on this matters to see if we can feasibly work this. So that concludes most of the talk. I'll touch on some small topics for just a taster for what's to come. So we want to increase the heat integration or advanced heat integration topics. So what we want to do is maybe also supply the cooling of a process from the cold side, but also see if we can design the PTES system in accordance with the PTES or with a process where we do the process heat integration simultaneously with designing the PTES system. As I said, we need to look at the turbo machinery effects on this, and then finally we're working on a dynamic model where we can look at how the system ramps up and ramps down, which is important to understand. For example, in this region, should use the thing again. In this region where, well, the terminal 55 shuts down and then the salt cycle starts up immediately. Well, that might not be perfectly feasible in a real world. So we want to see how effective that is in using the in this case. So that is, I think, yeah, the end of the talk. So thank you for listening. I think I didn't go over time, but I'll take any questions that you have at the moment. Thank you.
Are there any questions?
Just to start off, suppose I decide that this is a good solution for my house.
Yeah.
How soon might it be a feasible proposition for a domestic property, small domestic property?
So heat pumps by themselves are readily available in residential applications. We've been envisioning this more as an industrial application. So we didn't really look into residential applications, but I know that in and I'm going to pronounce this wrong, Ellsborg in Denmark, they have a district heating system that uses the same ideas, not exactly the same idea, but they have a supercritical cycle that they store the heat in, and then use that for their district heating purpose. So it wouldn't be, I think, implemented in your house specifically, but it would be implemented in a district heating scenario, and it is being implemented in Denmark, and then they're also repurposing a power plant in Alaska, and well, that's their only plant in that village, in that town. So they're repurposing that to use it as as an all-purpose heating supply. So it is being developed. I think it'll be available in the next 5 to maybe 10 years of fully or more widely available.
Is that in Aarhus? The location, is that in Aarhus?
Again, it started with E, and then it's like a harbor town. I can send you a link afterwards. I'm really bad with names, so I don't.
You had one slide where you started with 50, and then you went to 250, 260, and then just to cool it down again to 60. Why not just add 10 degrees there?
If you mean here,
Yeah.
that was just to demonstrate. It can go.
No, if there's, you had another one just back before that or after? This one?
Yeah.
So we're starting with 50, 200, 250, and then bring it to 60. And if that's the requirement 60, why not just add 10 there?
Because the inlet of the reactor might be, the reaction might be 200. It might be requiring a 200 degree inlet. So you're saying increase this to
60.
60 to 200.
That's it, stop.
No, this is so this reacts in the reactor. So this is product reactant A, and then it goes out to B. So it's not. It's a whole process. So I'm really simplifying it, but there are. I mean, it's just a representation. Am I understanding your question?
I think we're overcomplicating my question. My understanding was that the required temperature was 60 Celsius,
Yeah.
and our start is 50.
No, but this is ethanol, and that's carbon dioxide, for example. We're burning it. There's a reaction.
Okay.
So it's not. So I should have added more descriptives, but this is, let's say, reactant A. It goes through the reaction. It boils or just decomposes and then comes out here, and we need it at 60 degrees.
I think so. Fundamentally, the most desirable was with the oil. Is that what you use?
Depends on the application. The oil is so the oil cannot discharge electricity. So but the salt can. So or the salt cycle can. So it depends on what we want to have. If we want to implement this in a purely electricity in, electricity out case, so we charge with electricity, but we increase the thermal, increase the hot side, store it thermally, and then electricity out, then salt is amazing. But if we want to have supply heat, then we don't want to have that extra burden of discharging the cold side. So then we need to operate it as a heat pump with storage. So it depends on the application. In this case, yes, the oil. In this case, the oil operates better. But if we have a system where we have different ranges of temperatures, for example, the oil goes from 250 to 350 degrees. But if we have a process that has heating requirements from 250 to 350, but also from 350 to 450, then oil will not be able to supply that, and we will need to use the salt again for that higher temperature. So that's what we want to address. We want to hit as many of the temperature targets as we can. So that again gives us more cards to play with. Basically.
And what kind of oil are we looking at?
These are so heat transfer oils. So they are. So this is the name of the.
Sorry, is that a brand, Therminal?
Yeah, in terms of it's a brand. Yeah, and there's Dow-Therm. So they're produced by. I don't remember the name. I'll let you know.
Okay, thank you.
But yeah, these are brand names in Terminal, Dow-Therm. There are different applications for these. There are different temperature ranges that they can operate at. So there's Terminal 55, Terminal 66, 77. Yeah.
Yeah, thank you very much for the talk. You mentioned, and you started off with some slides in this second stage, talking about industries. And in your analysis, you bring out a whole different range of what you term applications, and obviously heat, temperature requirements. It'd be quite useful, I guess, to understand where you see this matching of those heat and cooling requirements across, mapping those onto those different use cases. Because I was struggling a bit to understand there what those, when you say applications, what those use cases actually were.
The applications for the PTES system.
Yeah. Obviously for the thermal, that's straightforward, but where you're all trying to combine thermal with cooling, which is what I understand to be the advantage of this integrated system.
Yes, so we want to address this medium temperature to high temperature region, so around 400 to 400 or 500 plus degrees of heating that we need to provide. So and then that brings us into industries like oil refining in that high temperature case, or it'll be tougher to do that. But glass manufacturing and cement production, those need sometimes open flames. But there are applications where this is used not in a not heating up a salt, but heating up a stove basically, and then you dip that in. So they're called copper stoves. So we want to operate within this region basically.
If I completely misunderstood the whole thrust of your talk, you're arguing this integrated system is where both heating and cooling are required.
No.
Completely missed the point of your talk then.
Well, I'm not sure. I'm not sure where I mentioned cooling.
Well, if you've got
That's here.
yeah.
So all right, that's I think that's on me. But so I just want to show this as a compound, the composite curves, to demonstrate what heat integration looks like in a process stream. So as I mentioned, we can have this internal heat exchange between the hot and cold sides, and then we can have heating requirements for the process and a cooling requirement for the process. So we're not targeting this side. So this I mean, we're just using the heating requirement of a process, for example. But again, your point is not exactly incorrect, where we want to be able to target that environment as well, but that's not what we looked at the moment. But if a process exists where this is the case, and if we can target this cooling, why not? But right now we're not looking at that.
So I was just wondering where in chemical industry, for example, you would have both of those needs.
I mean, I think this is from a simple process, but where it's again, when we do this heat integration, let's say we can cool it down to 60 degrees, right? But this is going to be, this is the final product that we have, so it's going to be ambient temperature. So we have, again, we cool it down from 60 to 20 degrees, 21 degrees. So that would be that 40-degree difference that we need to cool it down to. So that would be the cooling requirements. And then let's say this comes in at 20, but we need to heat it up to 50 for something else in the beginning. There's a mixing going on here. Then that also requires a heating that cannot be matched perfectly. Again, I'm making it up right now. I don't have a specific process in mind, but these are available in chemical industries where we have different kinds of requirements, basically.
Are there any corrosion issues? Temperatures and temperature cycling.
So in the working fluid, we only have carbon dioxide, so we don't really have that issue, I think. On the hot, I think that anything that would happen on the hot side. And it depends on the amount, it depends on the heat exchangers used and the tanks that are used. And we're basing this research or that side of the research off of research into concentrated solar power plants, which use these technologies, which use these heat exchangers. So I think it is proven in there, and then there might be some issues, but it's I think being handled on that side. We're looking at this more model building and control aspect.
I'd just add that the industry is moving away from salt solutions towards particle solutions.
Towards what?
Particles. So ceramic particles as a heat exchange medium.
I mean, that's also a viable option.
So you avoid the corrosion in that.
Yeah.
That's also a viable option. Just this. I had some background in molten salts. That's why I was kind of favorable towards them. But that's also a viable thing. And the problem there is those particle solutions are much harder to model than Aspen, because Aspen really doesn't like mixtures and particles in solutions. So it'll be if my goal or my idea is to build this model in a much more flexible software such as GPROMs or somewhere else other than Aspen, but currently that's the research that we have. But other oils or other applications can be used. Yeah. And the good thing with this is that once this is implemented, the storage basically can be switched out. So let's say it's been implemented 5-10 years from now, we see that, well, it's corroding too much. We find a new component or new heat storage medium. We can take out the tanks, take out only the heat exchanger, and don't touch the power train or the cold side, and we can replace whatever we have. So that gives us the flexibility advantage where the power train and the storage is decoupled.